Hi, folks. My name is Arul Verma. So this week we're going to be going over parallelism and concurrency in Rust, and this is lecture 11. So the goals for today is to talk about the motivation behind threads, how you spawn threads in Rust, and how you join threads. So first, let's talk about programming process. So what fundamentally happens when you run your programs in Rust? So what you have to understand is each program is treated as a process, and a process is an instance of that program that's running in the computer. So, and to be more specific, essentially your computer runs multiple processes simultaneously, and one of these processes is running your Rust program. In Unix and other operating systems, a process is generally started when a program is initiated. And let's be a bit more clear on like what a program really is. A program doesn't just refer to your program in code. Program refers to anything that your computer is doing. So the fact that Chrome is running is a program. The fact that I don't know, any form of background processes running like Edge, Firefox, Microsoft, Task Manager, basically any type of management your computer is doing of display resources or any resource of any type, it is being done in an independent process. Your Rust program is another example of these processes. When you run it, a process is started and for that program. But that's not necessarily always the case, but that's way out of the semantics of this course. The important thing to focus on is particularly for the focus of these programs, right? Like our Rust code, especially. How can we exploit the nature of these processes in order to make our program run faster? So there are three primary ways. And the first is obviously to have a bigger CPU. If we can compute faster, then obviously our code should run faster. Or we can have smaller transistors in CPUs and therefore fit more transistors in our CPUs. Because if we can have smaller electrical connections or our CPU can process faster, because it just has more capability to process, then our program would logically go faster and it would essentially run quicker. So there's a theory called Moore's law in electrical engineering, and the concept of Moore's law is the number of transistors in a microchip doubles every 2 years. And what this essentially means is your computing power doubles every 2 years. And you can see if you just follow this line that it's approximately true. But the problem with this theory is that especially as we reach an excessive number of transistors, that it's not only non-sustainable, but also transistors have decreasing returns in number of transistors. So as we get more and more transistors on a chip, it doesn't have as much impact as it did when we doubled from 1,000 to 2,000, as opposed to 50 million to 100 million. So Moore's law tells us that our computing power increases and the speed at which we compute goes up, but we have to look towards other ways to exploit essentially the nature of the computer to make our programs faster. So this is where we talk about multi-core programs and multi-core machines. So the concept of a multi-core is a core is just, it's equivalent to like a CPU. And while that's not an entirely accurate description, for the purposes of this lecture, it should be okay. The way it's most intuitive to think about, or I find most intuitive, is to treat the core like the brain of the computer. And that just means, and a brain is a singular piece of thought. So it's very easy to think of the core as a singular piece of thought that can be executed at a given time. So a core is capable of focusing on exactly one thing, and it does that one thing. And so a multi-core processor is an integrated circuit which has more than two or more cores to enhance performance. And these processors enable simultaneous processing of data with parallel processing and multi-threading. And each processor runs programs separately. Of course, you can run multiple processes at the same time. And in that sense, if you have multiple cores, each core can focus on a singular process, allowing you to do separate things. But the question is, how does this help speed up a singular process? If each core can focus on exactly one process at a time, then there's no efficiency being built into a singular process because a core can only fundamentally focus on one process at a time, or each processor program can only be focused on at a singular time. So having the capability to run multiple processes does not speed up a singular process. But that's not entirely true. And this is where we bring up the concept of threads. So thread is short for the concept of thread of execution, which just means the sequence of instructions that the CPU will execute. And it's useful when you want to leverage the power of multi-core systems to do one task. And the reason this is because each thread is treated as its own process to execute. Each thread has its own main method, and you can run a singular thread per core. And if you can run the same amount of code in one thread that you can in like your main or your general code. So this allows you to run the same amount of code multiple times. And this allows for parallel and concurrent code execution. And if you've already got the gears turning in your head, you kind of see what I'm getting at, but we'll elaborate a bit more as to why this is more efficient. So let's talk about first the definitions of parallelism and concurrency. Concurrency just means you're doing multiple computations at the same time, right? It's like if I'm juggling with one hand and I'm eating an apple with the other, I'm doing two things simultaneously. When you're patting your head and rubbing your stomach, that's a concurrent action because you're doing one thing with one hand and another thing with another. Parallelism is when you do the same task twice. So it's doing addition of 2 + 2 one time and then doing it again with another hand. So my left hand is doing 2 + 2, my right hand is doing 2 + 2. Or I'm eating an apple with my left hand and my right hand. So what is parallelism and concurrency then? So we can obviously, like previously, all our programs were sequential in execution. But if we think about concurrent but not parallel, this means that you have multiple programs running at the same time. And this kind of logically makes sense, right? Like you can have two different code Rust programs that you just hit run on and the computer will run them both. So that makes sense. That follows. So what is parallel execution then? Okay, and then given parallel execution definition, what would be parallel and concurrent? Well, parallel would just be to split up your computation into different parts. So say I had a calculator, right? So instead of doing like, and say they give us a complex formula of which it concludes with parentheses times parentheses. Because of how PEMDAS works, we can evaluate the two separate parentheses by themselves before doing the multiplication. So this allows us to split up the computation into two parts, and we compute the left-hand side times the left-hand side and the right-hand side inside the parentheses first. So, and those can run simultaneously. That would be a form of parallel execution. And you can do this by creating threads to solve each part and solve it at the same time. And this threads essentially just tell the computer that like create a new process and do this while we wait. And at the end, you just combine the results. So parallel and concurrent then would mean essentially just doing the same task multiple times and doing it concurrently at the same time. So when it would be an example of this, your computer does multiple tasks at the same time and like essentially running multiple instances of Chrome, running multiple instances of Firefox or whatever web browser you use. It also has your GPU and running your whatever your display is at the moment. So all of these things, it's managing multiple pieces of information at the same time. It's running multiple programs at the same time on multiple processes. And because they're happening at the same time simultaneously and they're often duplicate, that's an example of parallel and concurrent. So how do we spawn a single thread in Rust? Because this is the really important part, right? Like I can tell you this theory, but you have to know how to do it as well. So this is an example of some code to spawn a single thread. You have to use the crate std : thread, and then you go to main, you say thread : spawn, use the or symbol essentially, and you use the curly braces to make your main method. Use the semicolon to declare an end, so your thread's done, and then you print, and this creates a single thread. So there's a few things to go over here, and then a few things to unpack. The first is essentially this or symbol. And this or symbol actually doesn't really mean anything. The only thing it really means is that it's telling the compiler that like this thread is an independent main. It has its independent function and it's a temporary function. This function will not exist outside this parentheses of spawn. So it's just a form of saying this is a temporary function that you can treat as the main and after the end don't exist. It's the same as like saying fn main, but it's an equivalent writing of it. Don't actually try using fn main in here, that'll break it. Just use the or symbol, but intuitively, this or symbol just means this is the main of the thread. Now, you can see it says BUGGY on top. And the reason it says BUGGY is because this code fundamentally has a big issue with it. And let's go take a look at the issue in this sample code I've written that should emulate the same behavior. If I run this code, you'll notice that it says, intuitively, it should say hello world, then finished. But in reality, we just get finished. And sometimes we even get finished hello world. So why is that? The reason for that is because of how parallelism works. So threads run simultaneously as well, even compared to the main thread. So after I spawn this thread, this thread starts on doing this hello from another thread piece of code, while my main thread does the hello from the main thread. And because there's no consistency in which thread comes first, sometimes I do get my hello from another thread and then hello from a main thread, and then it'll end. Sometimes I'll get my hello from the main thread and then a hello from another thread, and then it'll end. Or what usually happens is because threads have significant overhead in creation, then, and you'll see that cost, especially with a simple program like the one I've showed you here, because that cost is essentially time. Creating this thread takes time. And because it takes time, usually what ends up happening is your main thread, after saying spawning that thread, this thread is still working on creating itself and making sure it's ready to go. And your main thread comes to the finish and it says, okay, I'm done. And then your program ends because you've reached the end of your code. So, and because your program has ended, because your main thread has finished, everything gets terminated. So all of your subthreads that you've created, they just instantly kill. So your program immediately ends there. So there are two ways to mitigate this, and we'll go into them in a second. But the important thing is you actually don't have to mitigate this in a long-running program. In something where you do multiple actions. In a program where you'll have like just two print statements to demonstrate the concept of threads, that cost becomes very noticeable because that overhead is very pronounced because we immediately end after the print. But in a longer program where you're doing some sort of like BFS or any form of algorithm, any form of for loop even, then you don't actually notice the difference in threads because there's very low chance of your main thread ending before your subthread gets to execute. So this is a better example of how we manage our threads to prevent that sort of main thread ending before our subthread finishes. And we do that with the concept of a join and a handle. So the theory behind this, let's start with that, is that after a thread is created, a thread is spawned, it returns a join handle for that thread. And remember in the beginning when we were talking about threads, we said that like if you have multiple threads, you want to join the results together. This is also how that kind of happens. So you create a handler for each of your threads, and that just tells Rust like this is where you'd get the results from your thread. And after a thread, and obviously you can return values from your threads as well. So after you create your thread, you spawn it, you do whatever inside, and let's say you return some value here. If you want to get that value out, you use your handle. So it's just standard convention to always have let handle equal thread : spawn, and then you create your threads. And then you can see we have something new here, which is our match. So there's a few things to unpack here. So we have our handle.join, and this call essentially just says, wait for our subthread to finish before progressing. And this is how we prevent our main thread from finishing before our subthread. Essentially what this tells our main thread to do is to stall until this handle is ready to join. Once it's ready to join, we join and then we progress. If we have OK here, that means our thread returned essentially nothing. But if our thread returned something, say we wanted to return some value, we could unpack that here using our OK. And we also have an error, which is our essentially backup for if our thread panics. So if you get an error in your unpack, that just means that when you were doing this thread spawn, your thread panicked in its entire. So that means you you tried to move data, you tried to borrow data incorrectly, or you just did something wrong in some terms of memory, and your thread panicked. And that's the only reason you'd be getting an error here. After you unpack your OK and your error, you can go on with your main thread, and you can see we print hello from the main thread, and we end. So this works. This is working code. And so there are a few things to know. We gave you the join and handle here before, but we never really gave it a name. The official name for this is a join handle, and it's a struct that gives you permission to join on a thread. And as I said before, it blocks the main program, or blocks the program essentially until the thread terminates. We also have our thread spawn, as we talked about, and it spawns a single thread and it returns the join handle. And we have our .join function. And this is essentially what our check is to make sure that our thread is ready to be joined together. So we go to the handle and we say, block where we are until the thread you're associated with is ready to go. And yeah, as we can see, if our thread panics, error is returned, otherwise we have our OK. So now let's talk about spawning multiple threads. Say we want to spawn 10 different threads in order to do our code. So intuitively, you'd think to do like a for I in 0.10, thread spawn, push our handles into like some sort of vector, and then we want to just join them and then unwrap. So this is just like our termination essentially to make it nice and clean. This code won't work. It actually isn't because of the for loop. You can actually do a for I in 0.10 and let h.spawn. And if we were to remove this print statement, or if we were to remove the variable I, this code would actually compile. However, if we were to maintain this I, such that we want to print exactly which thread we're in currently, this code would fail. And the reason for that is because of how memory works. If you were to try to run this code, I'm not going to because I don't have it open right now. But if you're trying to run this code, you'd get an error asking you to move the I into our thread, because the data I in our main thread does not also exist within our subthread. And if we try to use it within our subthread, I still tries to exist after, but our thread tries to delete that data, and that causes an issue. So to solve that, we have to use this keyword move. And we do this, let h equals thread : spawn, move, then we do the or symbol, as we talked about earlier, to create our main function. And then we put our print inside, and this code will compile. The reason this works is because the move keyword essentially just tells the compiler to take this I and to allow our thread to have a borrow on it. Not to have ownership, but to have a bar. So it can use the data and it can read it, it cannot edit. And we go into that more here, yeah. So we move our data into from our original thread into our new thread. Now for data that can be copied, the move keyword will either transfer the ownership of that data. So for example, if I have vectors or arrays, it'll transfer the ownership, or it will copy it. It will not clone it. It will copy that data into a new thread. So for integers, for example, they can be copied. So we can see that the move keyword copied that int I into our thread. And that's why when the thread terminated, that I wasn't deleted in our main either. So primitive types, obviously, are these things that you can clone, or if you implement you can copy. And if you implement a copy trait for whatever your data type you're using, you can use it here as well. So if we were to look at the two possible results from running that code, you'd see that we could get hello from thread 06145389720, 06543299718. And you'll notice that these are not identical. And the reason for that is because of how threads run. Threads do not run concurrently in the way that we describe them. They don't actually happen at the same time. The reality of how threads run is they both are being essentially decoded and are running, but the time of execution is not it's not sequential. It doesn't have to be sequential. So in one instance, they could be sequential, and they could also be simultaneous like this. But more often than not, when you run multiple threads, you get some sort of execution that looks like this on our bottom left, where thread 1 starts, then thread 2 starts, thread 3 starts, thread 1 resumes, thread 2 starts, thread 1 resumes, thread 2, thread 3, thread 2, thread 3. So you can see like it's a little bit mix and match piece by piece. It's not exactly one is running all the way through. And this creates a staggered termination time where we get thread 0 finishing because maybe it started first and it had the most amount of processing allocated for the most amount of time. And then thread 6 got a lot of processing for some reason next. Then thread 1 or thread 5, and so forth, so on. And it's not always consistent. If we were to run this 10 different times, we'd probably get 10 different results because of how exactly our computer's allocating resources toward cores in order to run these threads. So that's an important thing to understand about threads, that threads don't actually run simultaneously. And in reality, there is some sort of staggered execution, and you have to be conscious of the fact that your results will not be in order. So yeah, that's all for today. If you have any questions about parallelism or threads, make sure to come to us over the Discord and we'll go into more details. As a quick reminder, we are releasing Homework 8 tonight. And yeah, best of luck.